So, next let us discuss about the material properties at millimeter wave frequencies. So, first of all, we need to measure these material properties at different frequencies to characterize them. There are some popular methods used at microwave, millimeter or terahertz or infrared frequencies, and these methods are different at different frequencies. For example, at low RF or microwave frequencies, we use parallel plate method. We place dielectric material between two parallel plates for characterization, or sometimes we design some sort of resonators and then we measure the resonance frequency and other effects to measure the dielectric constant of any given material. So, we can still use that resonance method at millimeter wave frequencies also. So, other techniques are transmission line methods. So, for transmission line methods, what we do, we fabricate different lengths of transmission line. It can be, let us say, microstrip line which uses which supports quasi TEM up to different lengths, and then we simply measure the S parameters or scattering parameters of these two different lengths by using maybe some vector network analyzer. So, from the measurement of these complex scattering parameters, then we can determine what is the alpha or beta for that given transmission line, or what is the dielectric constant of the given substrate. Actually, if we further increase the frequency to submillimeter wave or to terahertz frequency, this transmission line method or that resonance method is not very accurate. There are some other methods which we use. So, that is terahertz time domain spectroscopy, but unfortunately it is not again very accurate method. So, we can determine the material characteristics at lower frequencies as well as at higher frequencies, for example, infrared or optical wavelength very accurately, but we have a problem from 100 gigahertz to 10 terahertz. We do not have any method which can give us very accurate sigma, tan delta and epsilon r values of any given material. So, that is why sometimes we call it a terahertz gap. So, whatever values I am going to show here, these are the approximate values, that is why. So, let us take some popular substrate material first. For example, the first substrate, it is RT 6010. So, Rogers suggests its dielectric constant at 10 gigahertz epsilon r equal to 6.2 and loss tangent that is equal to 0.002, but some other groups already use the same material at high frequency as high as 100 gigahertz, and they reported that the measured dielectric constant at 100 gigahertz of the same material is 7.4, and they also obtained a similar loss tangent value 0.002. Now, another popular material RT 5880. So, already we have seen the measured value as given by Rogers Corporation at 10 gigahertz epsilon r is 2.2 and tan delta is 0.0009. So, another group measured its performance at 60 gigahertz. For that they got epsilon r equal to 2.24. So, almost no difference, and tan delta it actually increases to 0.004. So, another popular material, it is quartz substrate. So, it is actually low loss substrate and very popular at millimeter wave frequencies, but the only problem is that it is fragile. At 10 gigahertz epsilon r equal to 3.8, even at 100 gigahertz no change. Look at the loss tangent value, it is just 0.0001, it increases to just 0.0002 at 100 gigahertz. So, it shows why quartz is so low, less lossy substrate. Now, we are doing one experiment. What we are doing? We are fabricating, let us say, one 20 millimeter long microstrip line, which is basically a form of transmission line on a 35 NQ substrate, and then what we are doing? We are measuring S21 and plotting it over the frequency range. So, look at the variation of loss. At 1 gigahertz, this loss is just 0.1 or 0.2 dB, and at let us say 20 gigahertz, it increases to 1.2 to 1.3 dB, but for the same microstrip line at 60 gigahertz, loss increases to almost 4 dB. What is this source of these losses then? As such, whatever material properties we have seen in comparison to 10 and 10 gigahertz and 100 gigahertz, that tan delta value or epsilon r, it is not changing as such, but if I measure loss, loss is increasing very rapidly with frequency. So, at millimeter wave frequencies, you see, if the loss is 3 dB, that means half of the power is already wasted, you are receiving only half of the incident power. Then there might be some other sources of losses. So, that we have to learn very carefully. So, the main point is that conductor loss, it increases with frequency. Not only that, we will see there is one more type of loss which we call the surface wave loss. So, before that, let us go through some other materials, popular materials. One of them is alumina. So, for alumina, depending on its purity, epsilon r, it can varies in between 9.6 to 9.9. I will show you the values of alumina even at terahertz it is being used, and typically its loss tangent value is 0.0001. This is most commonly used material for low cost fabrication at millimeter wave frequencies. Sapphire, typically at 100 gigahertz, again depending on its purity and composition, epsilon r 9.3 to 11.7, loss tangent 0.0004. So, it is one type of anisotropic material and not very popular. Then the fused quartz. So, its main advantage its excellent stability. So, quartz with different cut, it is called jet cut quartz. So, for this one epsilon r is 4.4, and look at their loss tangent values, it is very small. In fact, in this chart, this quartz material, they provide lowest loss. Then the popular artidiorite substrate, it is artidiorite 5880. So, typical epsilon r 2.2. So, this rexolite substrate 2.55, and for these two types copper clad substrates are available. So, that means the dielectric slab with top and bottom metallization. Then the PTFE substrate, Teflon as commonly called, typical dielectric constant 2.07 at 100 gigahertz. Polythene, it's a dielectric constant 2.3 and it's a polymer. We have also some others, TPX. So, TPX material is flexible material, and polypropylene, its dielectric constant 2.26, it is again another polymers. So, among there are many more. Among these, if you say which is the most popular material at millimeter wave frequencies, it is alumina, because its cost is very low. Now, in the previous one, when we are going through different dielectric, so that means we are considering mainly circuit design in printed circuit board technology, but we can design also circuit on chip. In that case, we have to use silicon, germanium or group 3, group 5 material. So, then let us see how this material they behave at millimeter wave frequencies. So, first of all, silicon or germanium, and typically when we consider N type or P type materials, it is a semiconductor materials. So, it comes with a finite sigma value. So, it is very lossy. So, we can't use the semiconductor materials as metal, or even we can't use this semiconductor material as dielectric, because if we treat the semiconductor material as dielectric, it will be very lossy. Already at millimeter wave frequencies, we have many sources of loss. We do not want to increase the loss further. So, then what is the option? How we can utilize this silicon, germanium or other group 3, group 5 materials? So, one thing is that we can use pure silicon, intrinsic silicon or germanium. So, in that case, we do not have any doping. So, its resistance will be high, and we can use that type of silicon or germanium as a dielectric material to design our components, how we do for PCB. So, with that silicon, only thing is that we have to add some metallization. So, this silicon or germanium, which is very close to intrinsic material, we call it high resistive silicon or high resistive germanium. So, let us see their material properties. So, semi insulating silicon, typical rho 2 into 10 to the power 3 to 10 to the power 5 ohm centimeter. So, this value is given at 10 gigahertz and its epsilon r is 12, loss tangent is 0.001, not bad. So, if I consider a typical value for which measurement result is available, rho is 8 into 10 to the power 3 ohm centimeter and the measured value is at 140 gigahertz, epsilon r is 11.7 and loss tangent 0.013, it is high, but still we can use it for circuit realization. You can compare this 0.013 value with the previous table. For all this dielectric, it's at least we have, let us say 0.003, we have a 0.00 factor and here it's 0.013. Next, semi insulating gallium arsenide. So, remember whenever we are using this word semi insulating, so that means it is more like intrinsic, doping concentration is negligibly small and we have to use special fabrication process to fabricate them. Conventional fab lab, they do not support this fabrication. So, semi insulating gallium arsenide, rho typically 10 to the power 7 to 10 to the power 9 ohm centimeter and epsilon r is quite high, 16. And if I consider a typical value, rho 7.8 into 10 to the power 7 ohm centimeter, for which the measured value is of epsilon r is 12.9 at 140 gigahertz, and the loss tangent is 0.005. So, if I compare the loss tangent value with silicon, obviously it is a very good substrate, almost like dielectric, but the problem is that it is very expensive compared to silicon. So, we can use for monolithic circuit fabrication, for both active and passive device fabrication. So, you see dielectric constant, let us say it is already 12 or more than 12. Now, what about the passive component size, let us say antenna dimension, and antenna its length typically is lambda g by 2. So, if I consider a 60 gigahertz design, wavelength, free space wavelength is 5 millimeter. At if I fabricate this antenna on gallium arsenide, so this is, it comes then 5 millimeter, 5 divided by root of 12 point something divided by 2, because it is lambda by 2. So, the dimension of this resonating antenna is so small that we can integrate this antenna on chip itself, and we can think of on chip antennas. Not only that, on chip antenna arrays, that is also possible at millimeter wave frequencies. Some other passive components which we will learn later, like couplers, filters, which uses the properties of transmission line and whose dimension again is determined by lambda g, sometimes lambda g by 2, sometimes lambda g by 4. So, those passive components also we can design on chip, because size reduces, it becomes a fraction of millimeter. So, in the same chip then we can design active components as well as those passive components like filters, couplers, and we can integrate them together in a single chip. So, next let us see how the properties of alumina, it varies with frequency. So, alumina it is being used not only at millimeter wave frequencies, as you see, look at the frequency scale. So, starting from microwave to almost 2.5 terahertz it is being used, and the refractive index, which is related to dielectric constant of this material. So, more or less it remains constant over this wide spectrum of frequency. So, we have they are comparing two values, one for this case 1 it is almost very pure alumina, 99.6% alumina, and the second one is 96% alumina. So, if I look at the epsilon r values, so it is more or less constant over this frequency range, and absorption coefficient, which represents actually the loss tangent. So, it increases, but not that bad, particularly if I consider below 1 terahertz. So, that is why this alumina is a very popular substrate at millimeter wave frequencies. So, now let us go back to the microstrip line example. So, after studying these material properties at millimeter wave frequencies, we see that in comparison to microwave frequency range or RF frequency range, loss tangent value or other properties, they do not change drastically. There is a change, there is an increment of loss tangent value, but it is really small. So, then if I look at the measured S21 or transmission of a microstrip line, what we see? We see that loss it increases rapidly with frequencies. So, then there might be some other sources of losses, and this loss is a function of frequency, which obviously is more at higher millimeter wave frequencies. So, sometimes this loss is so high, let us say at sub-millimeter wave frequencies, that we even can't use printed lines for sub-millimeter wave frequency range near 300 gigahertz. So, then what are these sources of losses? We will see one by one. So, the first one is conductor loss, sorry, here it is shown dielectric loss. So, dielectric loss, ohmic loss or conductor loss, and then the radiation and surface wave losses. So, if we design any wave guiding structure at millimeter wave frequencies, then obviously we have to use the complex propagation constant. We can't use the approximation of lossless line. We have to consider both alpha and beta. Alpha it represents the attenuation, and beta it is the phase constant. So, which is given by approximately twice by lambda g. So, for any given medium, if we know the mu, epsilon and sigma value, then we can easily calculate what is the alpha value and beta value of any given medium. Now, the power flow along a lossy line, let us say along the line we do not have any reflection, Pz, this is P naught into e to the power minus twice alpha z. We have a factor of 2 since we are considering power and not the electric field. So, this alpha and beta we can actually measure it by fabricating two different lengths of line. So, the loss whatever we have, it is then included in alpha, and if there is any phase variation or if there is any dispersion effect, that we can determine from the beta variation. So, then we see that alpha and beta both are very important parameters for any waveguiding structure. So, how to measure them? So, you see we have a relationship here. The leakage constant alpha, it can be represented in terms of the scattering parameters. If we have a section of waveguiding structure, then if we can measure the S parameters, let us say the S11 and S21, then from that S11 square plus S21 square, this is equal to e to the power minus twice alpha L. So, we can determine experimentally what is the alpha for any given guiding structure. Similarly, we can determine what is the phase constant beta by length difference method. So, what we have to do? We know that the theta due to a given physical length L, that is equal to theta equal to beta into L. So, now if we fabricate two different lengths, let us say L1 and L2, and the length difference is delta L, then the angle difference we can easily measure from S parameters, because angle of S21 that is nothing but the angle experienced by the signal from port 1 to port 2. So, from that then experimentally beta that is equal to delta theta by delta L. So, we see that we can measure experimentally both alpha and beta, and it will give you some idea about the alpha and beta. Now, obviously for any design, what we expect that alpha should be as small as possible, and what should be the variation of beta? beta is twice pi by lambda g. So, if I consider the frequency variation of beta, so this is twice pi into c by f. Okay, let us do in graph. So, beta, this is equal to twice pi by lambda g. This is the guided wavelength. So, twice pi, we can write down the velocity of the wave inside the medium into f. So, then we see ideally if I plot beta versus frequency, so it should increase linearly, and if there is any deviation from this straight line, so that means we have velocity as a function of frequency, we have dispersion effect. So, practically we deal with two important parameters. We usually plot beta by k naught instead of beta. So, k naught, this is equal to twice pi by lambda naught. So, it is nothing but beta in free space, and then we plot what is the value of beta by k naught and what is the value of alpha by k naught. So, if I plot beta by k naught versus frequency, ideally it should be constant, but for any wave guiding structure it actually varies with frequency. So, already we know what is fast wave, what is slow wave. So, let us say we have a rectangular waveguide filled with dielectric material, and for that we are plotting beta by k naught versus frequency. So, I am considering one example, a rectangular waveguide filled with dielectric material of dielectric constant epsilon r. So, if I plot beta by k naught for this given material, beta by k naught plot is somewhat like this. This dotted line, it shows the value where beta by k naught equal to 1.0. This diagram beta by k naught versus frequency is called the dispersion curve or dispersion diagram, and it provides many important information. For example, you see at this particular frequency, let us say FC1, it is starting from let us say 30 gigahertz, beta by k naught equal to 0. That means we do not have any propagation below this frequency. This is the cutoff frequency of that waveguide. Now, as frequency increases, beta by k naught increases. Now, at a frequency point here we have a crossing where beta by k naught is equal to 1. So, below this beta by k naught is less than 1. What that means? Beta by k naught is less than 1. So, that means we have Vp, phase velocity, higher than c, or we can call this left hand side part, this is the fast wave region, and the right hand side part for which beta by k naught is more than 1 or phase velocity, this is less than c, we call it the slow wave region. So, in this region, then my lambda g is smaller compared to lambda naught. So, component miniaturization is possible for the right hand side, while for the left hand side we can design one leaky wave antenna very easily. So, ideally it should be a straight line, but since it is changing with frequency, so that means it is dispersive. So, how dispersive this line is, we can understand it from that beta y k naught plot. So, you see then why this dispersion diagram is so important. We have so many information that what is the cutoff frequency for this given guiding structure, which range over what is the frequency range over which it behaves as the fast wave, what is the frequency range over which it behaves as a slow wave structure, then how dispersive this line is. Similarly, we may have another plot of alpha by k naught versus frequencies, from which we will have idea of how lossy the line is. If for a rectangular waveguide, if I plot alpha by k naught versus frequencies, it will be highest at cutoff frequencies, and actually it is infinity, and if I increase frequency alpha by k naught, it decreases with frequency. So, today we will stop here. So, in next class we will discuss the different sources of losses in details. Thank you.